Hey everyone, today for our video lesson, what we're going to do is we're going to move through the rest of Newton's laws and talk about equilibrium, which is sort of a neat sort of consequence of Newton's second law of motion. So let's go. We're going to start with Newton's second law of motion. I know we did in class the other day, but it was a little chaotic. That was the day the bell rang early, and me throwing things at you is not quite the same as really going over it. So for Newton's second law, basically the idea is this. Isaac Newton says that a force is required to create an acceleration. Kind of links to the inertia idea, right? Objects don't accelerate for no reason. They accelerate because a force does that to them. Now, he goes a little bit further and creates an equation for that. And his equation says that the net force is equal to the mass times the acceleration. A couple consequences here. It basically says that more force equals more acceleration. It means that less force is less acceleration. No force is no acceleration. But also, in here, it means that more mass would give you less acceleration. Which is something that you know intuitively. A heavy object is harder to accelerate. So to accelerate like a more massive object, you need to exert more force on it. And we did this kind of exercise in class, but we'll go back over it in a second. But also, it does something else that's kind of interesting. It defines the unit for force. So, in this equation, M stands for mass, which we measure in kilograms. A stands for the acceleration, which we measure in meters per second squared. And then F net stands for net force. Again, a force is just any push or pull. And this gives us a unit, or it's sort of a definition for what a force really is, though. If force is mass times acceleration, then let's think about what the unit should be. Now, I know I told you that it's a Newton, so yes, we can measure it in a Newton. But, like, where does that come from? Like, what we normally deal with kilograms and meters and seconds. Why are we suddenly naming things after people? Well, looking at that unit, if force is mass times acceleration, what really should the unit be? In other words, the unit for mass is a kilogram. The unit for acceleration is a meter per second squared. And so really the unit for force is a kilogram meter per second squared. That is the unit of measurement for force. Now, at some point, physicists, the people who came after and studied this, found that kilogram meter per second squared is just an annoying thing to say. It's an annoying thing to write. It's an annoying thing to type. They didn't have computers back then. So rather than calling it a kilogram meter per second squared every time we say this, let's just call it a Newton, and that's it. It also, I mentioned before, it sort of gives us a definition of what a Newton is. A Newton is the amount of force it takes to move 1 kilogram of mass with an acceleration of 1 meter per second squared. So again, that Newton, it's just a shortcut for this larger expression. I'll use them both throughout, class just to remind you that they both exist, but generally speaking, we would always use the unit Newton for force. So if you have like some exercise, what are the consequences of this equation? If the force from this hand accelerates a brick, and I know we did this in class, but twice the force produces twice the acceleration, right? Because you're pushing twice as hard. I'm sorry. Twice the force and twice the mass, so we're pushing twice as hard, but it's also twice as heavy, which give you the same acceleration. The same original force on twice the mass, so again, we're pushing the regular amount, but now it's twice as heavy, would give you half the acceleration. The same original force on 3 times the mass gives you 1/3 of the acceleration. Cool, that's it. I'm going to jump past 10 and 11. We did one of them in class. Again, I think I kind of threw it at you very quickly. But also, it's just so simple compared to what we have to be able to do that it's almost not worthwhile. I mentioned this net force, but what actually is net force? Well, a force is any push or pull, and you can have anything can create a force. You can pull something with a rope, or you can push it with your hand, or gravity can pull things, or magnets. But what is a net force? A net force is just another way of saying the total force. A nice way to think about it is this. You know the phrase net worth? Like, you'll see it with like celebrities or businesses or things like that, and you'll be like, oh, what is this person's net worth? That's their total worth. You add up all the things they own, you subtract all the things that they owe to other people, and that's their net worth, their total worth. Net force is your total force. But that doesn't mean we can just add all of these things up here. Because force is a vector. And vectors have direction, which means we need to consider that when we talk about net force. So, let's do some quick exercises here. I want you to actually pause the video here and see if you can do number 12. See if you can determine the net force on all of these objects. Go. Pause the video, try these on your own. I'm hoping you paused the video and tried them on your own. Let's go. A 3 and a 4 in the same direction gives you 7 newtons. They add together. But in opposite directions, they'll give you 1 newton. I'm going to actually add it. Oh, no, I just said magnitude, so I'm not going to do direction here. 3 one way and 3 the other way. Well, it's plus 3 minus 3, right? That gives you a total of 0 newtons. Okay, what if we have 2 dimensions? Well, we just wrapped up a unit on 2 dimensions, and every time we have 2 dimensions, like x's and y's, we deal with them separately. That's just how we do physics. So if we have 4 right and 4 left, what effects do those have on one another? They're just going to cancel each other out. How much net force, how much total force are we left over with? I think it's just the 3 newtons, right? Because the 4's cancel out. They go away. They're gone now. Over here, we've got 3 up, 3 down, 4 right, 4 left. I think that's a net force of 0 newtons. Perpendicular forces. Okay, well, we have a way of adding vectors at angles. We learned it in the first video lesson on tip to tail. So I'm going to do exactly that. I'm going to do that tip to tail. I'm going to redraw the 3 newtons here, and I'm going to draw the resultant force from start to finish. Let's look at this geometry here. I think that's a right triangle, right? And to find this, the resultant, I think we can just do a squared plus b squared equals c squared. I tried to keep this simple for you. This is an example of a 3, 4, 5 triangle. So 3 and 4 adding up, and again, something to point out here is that the angle really affects the math that happens here. We've got 3 and 4 that add up to 7. We've got 3 and 4 that add up to 1. And then we've got 3 and 4 that add up to 5. So we're going to be really careful with our directions when we go through this whole topic. And the most interesting one down here is, let's go back to what I just said. Whenever we're dealing with, 2 dimensions, like, up and down and then sideways, we're always going to split it into the x's, the y's, and we'll worry about everything at the end. So let's do the y's last, because the x's, there's a little more to it. Let's get it out of the way. I've got 6 left and 2 right. I'm going to just kind of, all right, what would those make? Well, I think those would make a total of 4 newtons to the left, right? Again, the 6 and the 2, they combine to make this 4. Now I'm looking at this example, and it looks awfully similar to that one, right? 3 up and 4 to the left. And in fact, if you tip to tail these guys, it is exactly the same thing. You get 5 newtons. So basically here we just added another 2 left, another 2 right, but the net effect of those, the total effect of those was nothing. It's essentially, effectively the same example twice. All right. So, true or false? If the net force acting on an object is 0, then there are no forces acting on the object. I think this is false. There's 2 examples of that. There was this guy right here, and this guy right here. They're both examples where there's multiple forces acting on the objects. There's things pushing it and pulling it in all directions, but they all cancel out for a net force of 0. So, 13 and 14, should sound familiar, actually. They're ripped right out of an old video lesson, but now we're doing forces, so I want to revisit it. Mr. Evans pushes a box with a force of 10 newtons. I'm fighting myself again. That was a mistake in the last video. Whatever, so we got 10 newtons one way, and in the opposite direction, we have 7 newtons. What's the net force is the term we would use here. Well, 10 one way, 7 the other way, and that's a net force of 3 newtons. Got dark here. What's the angle between these two? Well, they're in opposite directions, and so we would mathematically express this angle as 180 degrees. That's most of why I brought this up. I wanted to hit that idea again. Would this be the maximum or minimum resultant, or net force? The minimum. They're taking away from one another. Now, let's push one box with 10, and let's have me again. I'm just arguing myself here. Push in the same direction with 7 newtons. What would this net force be? Well, they're in the same direction. They'll add together. 17 newtons. What would we say the angle between these are? Anytime they're in the same direction, they're separated by an angle of 0. There is 0 difference in their direction. And this would be the maximum net force. Old ideas, but I like you guys seeing them pop up again. Great. So that's what net force means. What you're going to have to do with this, we're really going to, we'll get to those in class. But for now, as long as you understand that net forces cause accelerations, and that the net force is the total of all of these forces, then you're good for this idea. So far, we've only knocked down 2 of Newton. Oh, never mind. Yeah, let's do 15, 16. So 2 forces act on a frictionless block that is initially at rest on a frictionless surface. I want the speed of the block after 3 seconds. All right, we're initially at rest. And we've got forces. Forces cause accelerations. We want the speed after 3 seconds. All right, so the ones with the most accelerations will have the most speed. The ones with the least accelerations will have the least speed. We've got multiple forces here, so let's boil this down to make it a little simpler. What's the net force on all of these? Well, we've got 6 and 8. That's a net force. Since they're in opposite directions, they'll subtract. We get a net force of 2. Here, we've got a net force of, all right, 6 and 8. Well, that's the same net force. Here we've got, 6 and 8. That's the same net force. And here we've got, 10 and 10. That's a net force of 0 newtons. Again, we're going to rank the speeds of the block after the 3 seconds. All right, let's start with sort of the obvious one here. One of these blocks will not accelerate at all and will remain at rest, and it's D. Because it has a net force of 0. It's like playing tug of war and no one's winning. It's just not going to move. All right, now all of these other ones have a net force of 2 newtons, so it seems like they should all have the same acceleration, but look at these masses down here. Let's think about it like this. These 2 situations, B and C, are essentially identical, right? I think they're in opposite directions, but the magnitudes would be the same. So, which of these do you think would have less acceleration? The 2 kilogram ones or the 4 kilogram ones? I'm hoping you're saying the 4 kilogram ones. Because they're heavier. It's that simple. A heavy object is hard to accelerate. And then lastly, B and C are the same. So I'm just going to do B equals C. If you switch the orders of these 2, that's okay. So B is equal to C, which is greater than A, which is greater than D. For explaining your reasoning, I'm going to leave that one up to you, because we just kind of talked our way through it all. Shown is velocity versus time for an object that is moving in one dimension under the intermittent, so it's not always there, it's sometimes on, sometimes off, action of a single horizontal force. On the axis below, label the force versus time. Draw a graph representing the horizontal force. Okay, and I'm gonna make this the net force, just to clarify that for you guys. So let's go. Forces cause accelerations. 0 force causes 0 acceleration. So let's do this. Here, the velocity is changing. It has an acceleration. Is it a positive or a negative acceleration? I'm hoping you're telling me it's negative. So I'm just going to draw a negative line. Since the slope is constant, the force is constant. Cool. From here to here. What's happening to that velocity? Well, I think it's staying the same, right? And in fact, it has a value of 0. Okay, if it's staying the same, so basically let's do this. A equals negative, which means the force equals negative. Here, A equals 0, which means the force will be 0. Here, A equals positive, which means the force will be positive. I'm going to give it a higher force than this negative. And the reason I'm doing that is, see how this is steeper? I think that's more acceleration. More acceleration, more force. So I made this one like +4, whereas this one I just made -2. Those numbers came out of nowhere. It's a greater value. Here, this is, I think, the tricky part. What's the acceleration for this little part? Remember, acceleration is a change in velocity. The velocity is not changing, so this acceleration is 0, which means the force is 0. Forces cause accelerations, which are changes in velocity. Remember Newton's first law. An object in motion, without any additional forces, will remain in motion. And so this object was in motion, and it just stayed in motion, because there was 0 forces on it. 0 net force. Okay, that's Newton's second law. The important ideas there are force is, again, net force causes an acceleration. No net force causes no acceleration. That's the idea. Next up, let's see. Next up, Newton's third law. We'll do some equilibrium. Oh, let's do equilibrium first, because it's related. Okay, we're going to jump to equilibrium, and then we're going to do Newton's third law, because equilibrium is very closely related to the idea that we just discussed. So, I know I'm a little out of order, and I apologize. We're going to jump down to page 7, equilibrium. Equilibrium is is an idea that's very closely related to Newton's second law. Equilibrium is when the net force is equal to 0 newtons. It's called that because if you have an object and let's say it gets pulled to the right with, I don't know, 8 newtons, to make the net force 0, you would pull to the left with, you guessed it, 8 newtons. You see the equal values here? Equilibrium. But who cares, right? So what? The net force is 0. Like, why is this like a whole special page of my note packet? Well, the reason for that is, if F net is equal to ma, think about this for a second here. If the net force is 0, what does that mean about the other side of our equation? Well, the mass can't be 0. If there's no mass, the object simply doesn't exist, right? Because mass is the amount of matter, so the mass isn't 0. That means the acceleration must be 0. And so when an object is in equilibrium, it has an acceleration of 0 meters per second squared. So, we're going to talk about, again, really why we care about this for in a little bit, but when an object is in equilibrium, it has no acceleration. And the reason we kind of care about it is it makes an object in equilibrium, the problem suddenly becomes very, very easy. Think of this little, side example that I did. If I told you it was in equilibrium, you know that if there's 8 one way, there's 8 the other way. And there's really no math involved then. If I told you it was 20 one way, then there must be 20 the other way if it's in equilibrium. So, let's talk a little bit about objects in equilibrium. Are the following objects in equilibrium? If not, sketch and calculate the equilibrium, which I threw this into, again, our first video lesson. This is one force that makes equilibrium. So let's go with this. This first, all the way on the left, this one right here. Is this an equilibrium? No. The 2's cancel. I like that. The 3 does not cancel. So to put it into equilibrium, I'm going to add 3 newtons to the left. Cool. That's it. Right now the 3's cancel. We're all set. I want to come up to, I want to do this one actually last. For this next one, is this an equilibrium? I think so. I gave it a check mark. 2 up, 2 down, those will cancel. All the way on the right, are these in equilibrium? Well, 2 up, 2 down will cancel. I like that. But I don't think 3 right and 1 left cancel. To put it into equilibrium, I'm going to give it another 2 newtons to the left. Now you see how we have 3 each way? Those will cancel. We're now in equilibrium. It'll have no acceleration. Here, this last one. The reason I wanted to do this one last is, if you did this on your own, you might have done 2 and 2. But an equilibrium is by definition a single force. So if we want to cancel out 2 and 2, basically what I want to do is, I'm just redrawing that. I want to take this 2 and 2 and combine them into a single force. How would I do that? Well, we have a way of combining vectors, tip to tail. So we know that to cancel out like up and to the right, we should go like down and to the left, right? I think the direction is fairly intuitive. But to find its value, I'm going to do a squared plus b squared equals c squared. 2 squared plus 2 squared equals c squared. So that's, what's 2 squared plus 2 squared? I believe that's 8 equals c squared. Square root both sides, you get about 2 red 2. That's equal to c. Sounds a little weird, but there you go. So, talking about why we care what this object would be doing. Well, an object in equilibrium has an acceleration of 0. So what would the object be doing? Well, there's 2 possibilities. The object could be at rest. I think we all agree, right? An object at rest has no acceleration as long as it's remaining at rest. Or an object with 0 acceleration. It's possible it is moving. But if it's moving at constant velocity. So if you see either of these 2 things, at rest or moving at constant velocity, you need to be looking for that in a forces problem. It means that it's in equilibrium, the acceleration is 0, the forces are balanced. It's so important for these problems. To illustrate, 25, 26, 27, no, mostly 25, 26. A 5 kilogram block is being pulled across the floor in a straight line with a constant speed. That means we're in equilibrium. Explanation points of 10 meters per second. So the 10 meters per second does not matter. Doesn't matter. We're just interested in accelerations when we talk about forces. If the pulling force is 25 newtons, what is the force of friction? There are oh no, ruined it. I ruined the whole thing. There are equations for friction. They can be a little complicated. We haven't learned them. But we care about equilibrium because look at how simple this problem was. Once we realize it's in equilibrium, we know that if it's 25 forwards, it's 25 backwards. Done. Moving on. Solving for air resistance. All right, so if you solving for the drag force or air resistance requires years of calculus background. Which, if you're interested in learning about that, sign up for the AP Physics with Calculus course. A skydiver. Is there a skydiver? Falls at a constant velocity. Okay, so that means that gravity is pulling down on our skydiver. There's air resistance pushing upwards. If the gravity pulls down with 80 newtons, what is the value of the drag force? Well, we're in equilibrium, right? Because we're at a constant velocity. That means that its value is 80 newtons, and we're done. You didn't need to know any calculus. You barely need to know any math for that. Once you realize it's constant velocity, this problem is done for you. So let's get a little more used to identifying objects in equilibrium because it's really one of the most important tools we have when we talk about forces. For the following list of objects, check off the objects that have a net force of 0 newtons, which remember means it's in equilibrium. Objects in equilibrium are either moving at a constant velocity or at rest. 27. For this first one, I wish I was a little more specific. In a straight line. In a straight line at constant speed. So I was trying to make this an object in equilibrium. I'll admit I could have been more specific there. An object in free fall, is that equilibrium? No, because objects in the air accelerate as long as we neglect air resistance. A ball at rest? Sounds like equilibrium to me. It's not moving. A projectile, do those accelerate? They sure do. So this is not an example of equilibrium. A drag racer accelerating? Nope. Objects in equilibrium do not accelerate. Object at constant velocity, and this is our key phrase here. That sounds like equilibrium to me. All right, 25 minutes. I think that's actually a good length video. Okay. Let's do one more example. No, actually, let's do that one in class. You guys are good. As long as you took all these notes, that's what I wanted you to do. I'm going to call it here. I know I said we'd do Newton's third law, but let's just do that one in class because it's a little bit weird and there's nothing wrong with learning something in person. So that's it. See you guys in class.